Welcome to Pomodoro Joe for Tuesday, August 15th, 2023. Today we're doing LeetCode problem 86, partition list. This is a medium problem. Given the head of a linked list and a value x, partition it such that all nodes less than x come before nodes greater than or equal to x. You should preserve the original relative order of the nodes in each of the two partitions. Okay, so in the example here, the input is 1, 4, 3, 2, 5, 2. And x is 3. So everything less than 3 is on the left. Everything greater than or equal to 3 is on the right. So we have 1, 2, 2, and that maintains the order, and 4, 3, 5 maintains that order. Okay, some constraints, but I think this is fairly straightforward, so we'll put 25 minutes on the Pomodoro timer, and we will get started. So ideally, I only want to go through the list one time and move nodes around. So as I go through my list, I kind of have two choices. If I find something that is less than x, I can move it to the front of the list, move it to the left-hand side, but that means I have to maintain a head and tail for that side of the list. Or if I find something greater than or equal to x, I can move that to the tail of my list. And in that case, I only need to keep track of the tail, because anytime I find something greater than or equal to x, I just have to keep putting it at the tail. So I think that's my approach. I'll go through the list one time. When I find something greater than or equal to x, I'll put it at the tail of my list. Now, of course, I don't have the tail when I start out. I only find the tail when I get to the end. So I'll basically create a separate list that I'll call tail, or tail list, and it will keep track of all of these nodes that are going to be put at the tail. Then when I find the tail at the end of my traversal, I'll just put that list at the end of my tail. Okay. So let's do that. Let's see, what do we need to do this? Well, we'll need to know our current node, and we'll set that equal to the head to start. We also need to know the previous node. So as we move through, if we are going to remove a node, we actually have to have the previous node to reconnect its pointer. So I have to have the current node and the previous node. So let's have a previous node here. That's going to be none to start with. All right. Now I also need a place to keep track of this tail that I'm going to be building. So I'll have a tail list. And that's going to be none to start with. I don't know what nodes are going to be in the tail list. So as we move through, when we find a node greater than or equal to x, we'll add that to our tail list. And I'll need to know the tail list head and the tail list tail. So I'll have tail list head and tail list tail. All right. I'll need to keep track of the head so I know how to append this list to the end of my current list. And I need to keep track of the tail because I need to know where to add new nodes onto this list. All right. Now we just have to go through our entire list. So while we have some node, all right, if this node's value is greater than or equal to x, we're going to move this to the end, or we're going to put this into our tail list. So we have a couple different options here. One is if we already have our tail list, then we can just add this to the end. The other, we don't have our tail list yet, so this will be the first node in our tail list. Okay, so we have to remove this node from our list, and then we can put it into the tail list. So first let's remove the node. So to do that, we need to say the previous node next is going to be reconnected. Instead of pointing to this node, it's going to point to this node's dot next. All right, so that's effectively removed this node, although this node still has a pointer to that next node. So I want to set my next node to none, just to clean this up. Okay, so now we've effectively removed this node from the list. So we've removed our node. Now we need to put it into our tail list, if we have one. So let's check first. If we don't have a tail list head, then this node becomes the tail list head. And the tail list tail is also this node because it's the only node in the list. Otherwise, we have some tail list. So this tail list tail.next will equal this node, and the tail list tail will become this node. All right, so we've effectively removed our node from the current list. We've put it into our tail list. The next step will be to advance our node. So in that case, let's see, if we have a previous node, so what we really want to say is something like node is equal to node.next. But we've just removed our node from our current list. It doesn't have a next anymore. So we might want to keep track of what was our next node when we entered this. So let's do that here. Let's say our next node is equal to the node.next. Then we can actually set this equal to the next node. All right. And then this will be equal to the next node. And the previous node doesn't actually move because we've removed a node, so the previous node stays the previous node. All right. Now, if we don't have a node with a greater value than x, greater than or equal to x, then we can just move on to the next node. So node is equal to node.next, but before we advance that node, we have to set our previous node. So the previous is equal to this node, and then we advance our node to the next. And this should go until we reach the end of our list. All right, now we've reached the end of the list. We need to take our tail list and attach it to the end of our current list. So what's at the end of our current list right now? Well, the tail of our current list is this previous node because our current node has gone off the end of our list. So if we have a previous node, then the previous nodes.next will be the head of this tail list. Okay, and if we don't have a previous node, that means we don't have any original list anymore, and our entire tail list will become our result. So in that case, we'll just set our previous equal to the tail list head, and here we can return the previous. That's our result. All right, let's run this and see if it works. All right. Oh, I didn't call it previous node. It's just called previous. All right. Where else did I mess up? Try that again. Right. We might not have a previous node. Okay. So if we get a node where the value is greater than or equal to x, we don't necessarily have a previous node. So let me check that first. If we have a previous node, then we can set the previous node next to the next node. Try this again. And we have an error. What do we have? 1, 2, 2. It looks like it's expecting 1, 2, 2, and I just have the end, 2, 4, 3, 5. So that means I didn't have a previous. So I think what's happening here is I'm losing the head of my list. Yep, that's actually is what's happening here. So what's happening here is I'm losing the head of the list. So I actually need to keep track of the head of my current list. So let's have a result. That's equal to the head of the list. All right. So the result is equal to the head of the list. If we have a previous, then we move on. All right. If we don't have a previous node, in that case, our result has to be equal to this next node. Okay. That's the problem. Let's run that. It still doesn't work? What? Oh, of course. I have to fix up the end. So we should be returning result here. All right, so if we had a previous, then we'll add this to the end. Otherwise, we have our result, and that's just going to be equal to the tail. Oh man, I've thoroughly screwed this one up. Okay, that's passing. Let's submit and see how we do. And I think there's a better way to do this, actually. Okay, so this works. And we beat 75% for runtime and 55% for memory, so not too bad. So this works, but I think there's a better way. This is actually pretty complicated. Let's start this whole thing over. All right. Instead of doing this where we're actually keeping track of our original list and this new tail list, Let's just keep track of the left and right partitions. So this already says we need to partition into two halves, or two partitions. One will be the less than partition, the other will be the greater than partition. I'll call it the left and the right. So essentially, let's just start with two blank lists. We'll build up the entire left list, we'll build up the entire right list, and then we'll just stitch the two together at the end. I think that's way easier. So we'll have the left list, or left head, and that will be none. And we'll have the right head, or I'll do left head and left tail, and then right head, right tail. Okay, this will be way easier. And then we'll have our current node, so I'll just have node, and that's going to equal head. All right. I think that's all we need. So while we have some node, okay, we'll check to see if this node has a value greater than or equal to x. So if this is greater than or equal to x, then this node will go into our right list. So let's make sure we have one. If right, or let's say if not right head, then right head is equal to this node, and the right tail is equal to this node. Otherwise, we have a right list, so we can just extend it by setting the right tail dot next equal to this node, and then the right tail becomes this node. Great. Otherwise, this is a node that has a value lower than x. So this will do the same thing, except using the left list. So if not left head, and then of course we need to advance our node. All right, now at the very end, we can just stitch the two nodes together, but only if we have a left node. So if the left head, or I should say left tail, it doesn't really matter, but if we have a left tail, then left tail dot next is equal to right head. Otherwise, our left will actually be our right. We only have a right list, basically. So the left head will equal the right head, and we can return the left head. All right, so this is very similar to our previous solution, but instead of building up two separate lists where we have our original list modified and our new tail list, we're just going to have two new lists, a left list and a right list. Let's see if this works. Oh, so it found a cycle, and that's because I wasn't cleaning up. Of course. So I can't just set these nodes like this. I need to clean up the nodes. So I need to disconnect the nodes from each other. All right. Let's grab the next node right off the bat. The next node is the node.next, and then this will just be the next node. And next, let's clean up this node. This node.next equals none, so it doesn't point to anything. Then we can reconnect our node wherever we want, and then advance our node to the next node. Try that one more time. That just illustrates the importance of cleaning up your pointers. All right, let's submit this and see if we do any better than our previous solution. And we do exactly the same. We beat 75% for runtime and 14% for memory. So in fact, we did better with our previous solution in terms of memory and exactly the same in terms of runtime. So the previous solution might actually be better. Okay, this one is a lot cleaner though. I actually prefer this solution. It is cleaner. What else could we do to make this faster? Well, let's see. So we could flip around some of these conditionals. That might be worth a shot. Yeah, let's do that. Let's do if this is less than x, and we'll flip these around. Let's do the left first and then the right. So this is sort of supposing that doing a less than is a little bit faster than doing a greater than and equal to. Okay, looks like got that off just by a little bit. And that's actually slower. So that doesn't help us at all. All right, we could also try things like this. Swap these around. That's a lot better, actually. We're at a 91% for runtime and 84% for memory, so that actually helps a lot. I guess doing the comparison for if it is something instead of if it's not something, it's a little bit faster. I'm surprised by that, but hey, I'll take it. All right, we're low on time, so that's it for me. Hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.